Thanks, Ed. It's really a pleasure to be here. I am also, some of you may know, I'm on the board of NYSERDA. And we had a meeting earlier this week on Tuesday in Albany at which we approved the strategic outlook for the next 4 years. And if you think about it, the challenge that the governor has put forward in trying to reduce greenhouse gas emissions by 40% below 1990 by 2030, 50% renewables, 23% reduction of energy consumption in buildings below 2012 by 2030. Those are pretty ambitious goals. How do you turn those goals into missions and programs and activities that align what you do with the progress that you hope to achieve? And so what the board had asked management was a better alignment of strategic goals with the various missions and with programs and market development and research and innovation to get you there. And I call your attention to this because some of your conversations later today, if you think about how do you achieve those goals with the overlay of climate change and the kinds of challenges it presents for not just grid modernization, but resilience of the grid, energy efficiency improvements, and all the things that we hope to achieve, it gets increasingly more difficult. So some of your conversations are going to be extremely important for developing the kind of programs that we need to get there. I call your attention, Janet Joseph, who spoke here last year, gave a terrific talk about the strategic outlook to the board on Tuesday, and if you have a chance, you should take a listen to that. Janet also mentioned here last year and again to me this week that the COE is uniquely positioned in this space of energy systems within the state, because remember, all of this activity is focused on the state. Particularly in the industry partnerships that it has developed over the years, and the notion that most of this agenda cannot be achieved without the kinds of partnerships with industry across, that's no single industry, no single college, no single department, no single university for that matter, can do alone. So COE is uniquely positioned to pull together these teams and to get this job done and to really push at the boundaries of this work, which is a good segue to pushing at the boundaries, because our first speaker, Michelle Addington, has been really challenging a lot of the basic assumptions of our energy policies and pushing the boundaries of energy systems, advanced materials, and new technologies over her career. She's trained as an architect and an engineer, which is perfect for this group. She's a professor at Yale and has a joint appointment in the Yale School of Forestry, Environmental Studies. She came from Harvard. I'm a Yale alumnus, so I love it when somebody leaves Harvard for Yale. And that actually, that intersection, I imagine, is quite rich for you intellectually. So without further ado, Michelle Addington on new technologies of the past and the future.
Thank you so much. I'm actually thrilled to be here. It's been a long time since I've been at Syracuse, and this is going to be my first opportunity to see your new building that was done by a dear friend and former colleague, Toshiko Mori. So I'm quite excited about being here, but also really excited about the schedule that you have today, and just sort of wish I could split into 3 to go to all the different sessions. I also have to start with a little bit of an apology. I really always think that anyone who is a keynote speaker needs to come to the entire symposium. It's important to sort of understand the scope of what they're dealing with, is to understand all the different points of views. One of the reasons why I originally said I couldn't do this is because I knew that I would miss yesterday. And I'm heartbroken about the fact that I missed your keynotes yesterday. I would have loved to have been able to have referred to them today, so that's an apology for me. I teach until from 9:30 to 5:30 on Wednesday. It's my big day, and I just I can't cancel classes. That was my commitment to the students this year, that this was to be the first year I would never cancel a class, and darn it if every opportunity that I've had for the fall would involve me canceling a class, so I've been holding true to that. One of the things that I really key to talk about in all of this is it's, unquestionable that I love technology, that I love advanced technology, that I love new technology. But I spend a great deal of time questioning not technology itself, but the way that we deploy and that we think about technology. And that's very much what this talk is going to be about, sort of challenging a lot of sort of rather convenient and ubiquitous assumptions we have about technology. If we think about, and I have to put my glasses on, they haven't really improved this technology all that much. Forward is probably the giant green arrow. Yes. So like a lot of you in here, I was one of the first on board to get my Echo. And if we want to think about it from saving energy, and all the possibilities for it, really the primary energy it saves is that I get to lay in bed and give it instructions. So it does keep me in bed for another 10 minutes in the morning and so on. And then when I realize I haven't set my alarm, I don't even have to roll over in bed to set the alarm. I just sort of shout at it to set my alarm. But we look at things like this and we think about as well, the Apple Home Kit and all the things it was going to automate in a home, the locks, the lights, the thermostats, and so on, the Google Glass, the locks, the lights, the thermostat, the Microsoft Home of the Future, the locks. As you approach the front door, the lights come on, you hear a click as a door unlocks. Very similar to the Philips Home of the Future from 1987 as a front door. In this case, it's a woman, so the other case it was a man. She is recognized by an intelligence system. The door alarm is switched off. The door unlocks and opens, which is very similar. Some of you might have been familiar, not with the movie that came out using the same name, but the original company, the Tron hyper-intelligent building of 1987. From the moment the employee arrives at work, the building systems recognize him, which of course was featured as well in the 1967 CBS Evening News, Home of the 21st Century. As a guest approaches the front door, they'll be recognized by the cameras, and we can keep going back. Sort of this idea of automating, or how much of our technology is spent automating the known, automating what it is that we already do. Very little of it sort of like stepping back to challenge now that technology has developed in a particular way and evolved in a particular way. What else could we be doing? But very much of it is sort of identifying the way that we do things and trying to improve them. And so I would say that we're in a state of technological subordination, and it's not this subordination, not that we are subordinate to technology, but rather that we've held our technology subordinate to very common and standard beliefs we have about the way that things work. And this is sort of the challenge that I want to put forward to you today. I'd say in no place and in no area is this more a pernicious problem than the problem of dealing with energy in buildings, particularly environmental systems and lighting systems in buildings. Sort of our idea of what is the standard that we are working toward, that we're trying to improve, is actually constraining the technological development that we do in those areas. One of the things I find particularly fascinating when we think about environmental systems in buildings, and we think about the sciences that deal with environmental systems in buildings, is this is a case where the science is younger than the technology. We look at sort of the principles of heat transfer and fluid dynamics. We generally say that with the development of boundary layer theory at the beginning of the 20th century was when the theory finally sort of began to come into place. It wasn't until really the 1950s that we had equations for this. It was the development of computational fluid dynamics in the early 70s that we actually could practically start to solve these. They're still some of the most difficult equations to solve in the world. But the reality is that it was the last branch of classical physics to have a theoretical structure that could match empirical observations. Comes in the 20th century. The way that we condition buildings comes from the 19th century. And everything that we have done with that technology has related to beliefs that developed in the 19th century about how air moves. Some of it somewhat nonsensical. We have a whole sort of set of treatises at the beginning of the 19th century. This is the beginning of what I call the smart arrows that show up in pretty much every architectural diagram, that if indeed I draw an arrow, this is where wind is going, where ventilation is happening. And in some very bizarre cases, arrows pretty much anywhere also indicate where the sun might be coming from, even insofar as not likely on that. But this sort of like the beginning of this is sort of the beginning of the 19th century, this very sort of strong belief that one could diagram and show how air moved. Things that were so profound that something like this, and anybody who really knows their fluid mechanics knows that this is not possible without a great deal of other things happening to make this so, this sort of thought that we're going to have that kind of circulation in that way. And you can explain it rhetorically, but physically you cannot. Something else has to be happening in order to do that. And yet that belief that this is how air moves is so strong that often people use it as boundary conditions in order to define how, whether it's different types of simulation programs or also when they're examining their technologies, they expect their technologies to perform in the way that they believe things should be performing. They're actually sort of constraining the way that we go forward with this. One of the key things that happened in the 19th century was there were going to be two bouts of what I would call anthrophobia, sort of fear of people. The first one was a fear of people's toxic emanations, very profound throughout the United States as well as in Great Britain. This terrible fear that if you smelled any kind of body odor was an indication that the body was putrefying, and therefore any kind of proximity to that means that you too were going to die. So the title of this lecture series that took place, the Franklin Institute in Philadelphia, Man's Own Breath is His Greatest Enemy. We laugh at this now, but this is why we have dilution-based systems. Our environmental systems, our primary environmental systems, are dilution systems. The dilution systems were based on this idea that people's emanations, their breath, their body odor, were deadly poisons, and what you needed to do was dilute that. We today use a dilution system, and it continues on. The sort of the second bout of anthrophobia came about with the 1918 flu epidemic, and again, this sort of push for cleanliness, for perfection, that we had to sort of create this environment that not only sort of like diluted the emanations, but then the second layer that came onto it is that it needed to be homogeneous. It needed to be sealed, it needed to be protected. So we are left based on very bizarre beliefs about health, very bizarre beliefs. There's a whole series of sort of other trends that come into play. We are left with what we should know. Everybody in here who studied a little bit of science, a little bit about how the body works, should know that, the thought that the ideal surround, the ideal building environment for the human body is this completely homogeneous, sealed environment of a single sort of set of conditions, of humidity, of temperature, is about as bizarre as it can be. And yet, for all of our technological development, we continue to sort of operate subordinate to the belief that that is the standard. We look at technologies, particularly in terms of control systems and sensor systems, in order to sort of make it sort of the delivery of that environment more and more efficient, without anyone ever stepping back to question, why on earth are we doing this? Why does my body care what that temperature is? Actually, why does my body care what that temperature is that's about a centimeter away from my body? It actually doesn't. If we look at how we spend energy in buildings, the amount of energy we invest into a system that really has very little to do with how the human body actually performs and how the human body is engaged in the system is quite bizarre, but we choose not to question that. So incredible development technologically to optimize the systems we have, to improve the efficiency of the systems we have, but nobody's stepping back to say, why? Why on earth are we privileging this type of system? And so we start to think about this. We look at the air handler that was patented in 1911. It's the same as the air handler today. Yes, there's a cooling coil that was added to it. Yes, the controls have radically improved on this, but it is the same sort of physical set of operations that take place. You can't think of other branches that we have in science and technology where the technology outdates the science. You know, we think about scientific, scientific theories as sort of being incredibly long-lived, sort of primary ideas, governing principles that are very long-lived. We expect that technologies, emerge, evolve, become obsolescent, and ever rapid cycles, incredibly rapid in many fields. This is one where the science is evolving and has evolved, where the technology has not evolved. And I often think that one of the reasons we're caught in this is actually sort of like how it all came together in the air handler, and that particular approach was really kind of ahead of its time. It was really quite masterful in the way that it dealt with all of these different heat transfer behaviors. That might be one of the reasons why, it had such legs within it, because it really was quite advanced for its time. But it's not advanced for our time. It's time to let that one go. And instead, what we see is, this is just a small jump from, and those of you who work on HVAC systems would probably recognize some of this. We have a building at Yale, Kroon Hall, which is supposed to be, I believe that many times they have managed to put it in different alumni magazines, et cetera, as I think I've seen it called the greenest building in the world. On campus, we're not sure it's the greenest building on its block, but it has shown up as the greenest building in the world. Elaborate systems, high-tech systems. It was supposed to be showcasing every sort of advanced technology. And the complexity of the systems are such, this is just one of 57 pages of data about the HVAC system that comes out every minute. And the thought that there is some kind of incredible brain out there that's sorting through all of this is very much part of this belief that somehow we can optimize this if we just have better controls, if we just have more sensors. And in the case of Kroon Hall, as what we have with many other buildings like this, if people would just behave better, if people could just be trained to behave properly in the buildings. It's an odd thing when we think that the environmental systems in buildings, which exist only, with the exception of laboratories and certain medical facilities, exist only to serve the building, when people become the problematic perturbation that are disrupting the operation of my building system, that's when things have gone quite backwards on that. It's true with lighting. Lighting has an even more bizarre history. The reason why we have even light levels and we design for even light levels comes from the desire to disrupt and bankrupt German industry as part of the leading up to World War II involvement in there. The major companies were required to have fluorescent lighting and sort of ceiling-based fluorescent lighting ready for the 1939 World's Fair. You may not be able to read what this says on here. This is 1942. Actually, now I have to get up to read it. So this is 1939, fluorescent lighting is introduced to the United States. By 1941, the business was $250 million. In 2 years, $250 million, 1941 dollars. That's astonishing. And there was part of a series of very concerted efforts to force building owners and force building designers to switch to a system that at the time brought requirements that you actually had to reinforce your ceiling in order to deal with the big heavy ballast, that nobody particularly wanted that kind of evenness in terms of lighting. It has absolutely nothing to do with the way that the eye sees, and yet that is precisely the kind of lighting systems that we're left with today. Again, this one had, at least the environmental system was born from, while it may not be legitimate now, but certainly at the time was considered legitimate beliefs about human health, this had nothing to do with how the eye saw. It really was a political strategy, a political and economic strategy that took place. And so we're caught with things like this today. Now that I'm at Yale, I always have to use, besides, I'm sorry I picked on Kroon Hall, now I will pick on the School of Architecture at Harvard. This was part of an energy efficient lighting retrofit that they did. After they did the retrofit, before the retrofit, only 1 out of every 3 of these was lit. They replaced them with the most efficient fluorescents at the time. This is now probably 20 years old. And it didn't matter where you were in a building, deep in the bowels of the building, where people couldn't go, whether it was circulation space, you were next to glazing, whether you were in the stacks. It's exactly the same lighting. This sort of belief that we have to provide a standard level of lighting, we don't question. Amazingly, that we don't question. And such that even when we had something like LEDs, LEDs should have been a huge game changer for this. Radically different approach, particularly in sort of like getting us away from ceiling-based lighting, and yet we have been pushed into sort of like using them as replacements for our existing technology, pushed into sort of like seeing that they match the conditions of fluorescence or high intensity discharge, or that the smaller ones, are direct replacements for what we're familiar with. A technology that unquestionably could have been a massive game changer for us, and yet we're still kind of restricting it to sort of fitting in with our normative belief about how things should operate. Even when we step into facades, sort of like the incredible opportunities that we found from the advent of different types of glass manufacturing from the 19th century, so the opportunity for glazed facades. We also now accept the glazed facade as something that's prima facie, that it's good for us, that it brings all kinds of things that we want, that it brings view, it brings light, it brings heat, or not within that. And again, in the same way that we've dealt with our other things, in order to deal with the fact that it also brings a lot of problems, we continue to engineer that facade, add more and more functionality to the facade, add more and more layers to that facade, but sort of work on that facade to sort of make sure that we've mitigated some of the very problems that we have created simply because we chose a glass facade or a glazed facade on that. I'm looking here now from the Department of Energy, and this is actually something, a mantra that you see a lot when we talk about glazing, this sort of, as you see in this first couple of sentences, the desire that, the ideal glazing is one that lets in heat gain in the summertime, but does not bring it in the wintertime. This has been a lot of the push for dynamic facades. Well, interesting enough, if you look through indigenous architecture, there is no major trend, climatic trend in indigenous architecture that has ever brought in the sun in the wintertime. None. That actually is also a 20th century idea about how we should be dealing with the heat of the sun in the summertime. It's very, very difficult to utilize the heat from sun in the wintertime in any kind of sort of building circumstance. Again, the other things that you would have to do, and there's often much better ways of handling that and utilizing it than bringing it in through a glazed facade. Yet this sort of belief that we have to sort of have this facade that's going to do exactly the opposite at different times of the year has led a lot of this. This too comes from an interesting time in history. We can think about this image from Le Corbusier, L'été l'hiver, that, you block it all in the summertime, you let it all in the wintertime. Of course, the stuff coming in the wintertime is instant glare, coming straight in. And again, there's going to be another set of overlays that often happens in order to deal with the fact that, gee, that darn direct sun actually is very problematic from a vision standpoint. Very little has gone into questioning why is it that, we think that the picture plane is a place to deal with heat, light, both heat in both directions, light in multiple directions, as well as view. It's actually not good for any of those, much less good for the combination. You can deal with heat, light, and view many other kinds of ways, many other kinds of systems, but the fact that we want it all to be assigned to our facade is, again, sort of part of our desire or part of our connection to that which is prima facie on that. So I'm going to put forward sort of in my time two basic sort of things that I want you to remember from this sort of quick ride through of history on this. The first one is both of them relate to the idea that part of the way that we think about energy in buildings is very building centric. We do energy balances on buildings. Again, I find that bizarre. A building is not an energy system. It's a unit of private property. It is not an appropriate place to do an energy balance. You can do an energy balance on specific pieces of equipment, certain types of operations, but you don't do one on a building. It's a collection of many things that intervenes on much larger things. When we do energy balances around buildings, and I'm going to create at least half the room full of enemies here. I already know that. I probably should have had an earlier flight as a result. But net zero energy is something that the intention is wonderful. The physics of it are really problematic in that we are truncating the building from some of the most complex situations that it involves in. We're eliminating a lot of the actual sort of energy impacts that it has. We're taking everything and we're taking small things, scaling them up to the building. We're taking large things, simply lopping them off and not including them. The intention is good, but it's not going to be additive. In many ways, it's a little bit like a perpetual motion machine when you leave out these other things, and I'll show you in a minute why they can't be neglected. So the first thing I'm going to suggest that we do from the big end of it is decoupling energy systems from thinking that they're about property. They might be about property from a financial standpoint, from a jurisdictional standpoint, but they're not about property from a physical standpoint. And the other thing, and this is probably get my political leanings here, energy supply should be a public service, not a private privilege. One of my biggest objections with Kroon Hall is that here we have our campus, our Yale campus, which has all distributed power, except Kroon Hall wants to have its own systems. Kroon Hall, dug 40 boreholes for its own geothermal system. It turns out it takes way more energy to pump through the closed loop geothermal system than it did just to sort of tie into the central steam and chilled water plant. Way more energy. But regardless of that, this sort of idea that each building can be responsible for its own energy system, purchasing its own energy, it works for those who are wealthy. It does not work for the public at large, but it's also not very good from a science standpoint. You want to optimize your generation at the appropriate system scales. You want to strategically intervene. You still act. And so the point that I want to bring forward here is that the building is not an energy system. It's not the unit at which we balance. It is a unit in which we build. It is a unit in which we intervene. So we understand the analysis at the different scales. We then have to understand that we still take action through a building. So that doesn't mean that we don't necessarily bring energy to buildings or energy generation to buildings, but we bring energy generation to buildings when it's part of understanding how the larger network operates, how we optimize the larger network, not how we optimize the building on that. And then the last one, which I would hope most of you are familiar with, about exergene matching generation to consumption. It's always troubled me that in so many of our discussions about building, we don't work from the dumb basic up. We work from the sort of like the smart down, but we don't work from the dumb basic up. The idea that for all of your different kind of generation systems, that they can fulfill different types of needs. Alternating current is like the universal donor in blood. It does everything for us, which is why we tend to hyper-focus on that, because it does everything for us at enormous energy penalty. While each one of these will sort of like handle different aspects in a more effective way. I think the screen is a little bleached out, so you're sort of missing the fact that alternating current really is doing all those. But if we start to think about the potentials that we get from this, one would hope that as we design, we work from the bottom up. We handle the things that we can do very well at building scale, and dealing with thermal mass at building scale is something we can do that analysis at building scale. We can analyze alternating current at building scale. So sort of working your way on up, invest in your technologies in an appropriate type of fashion, as opposed to sort of like thinking that I just sort of really need to focus at the top in terms of my energy generation on that. Another thing I'd sort of want to encourage us to do is be causal, to deal with causation. This is one of many things that you will see on a regular, have seen on a regular basis, looking at radiative forcing. When we think about climate change, it's not just about greenhouse gases, and it's particularly not just about carbon dioxide. It's all about radiative forcing. It's all about the contribution of every one of these things to sort of shifting what that thermal balance of the Earth is. We play a role in most of these. We play a very large role in albedo. Albedo ends up being one of the least understood aspects of radiative forcing. So many of the things that we're doing by only focusing on carbon dioxide and not looking at these others means that so we're not dealing with all of the consequences of our building. And of course, part of what comes up from this is often consequences of our building. Our building is in a particular property location. Often the consequences of decisions we make are disconnected from that. It's really easy to talk about energy generation and related to carbon dioxide becomes more and more difficult to look at these other aspects. But if I could encourage us to do anything, is to keep our eyes on the prize. And the prize is radiative forcing. If we could start to look at a metric that actually connected us to radiative forcing, I think we would go a long way in really having our buildings be more effective. Embodied energy tends to be something that falls very much by the wayside. There's a whole group of people interested in life cycle analysis who talk about this. But on the whole, when we start talking about things like net zero energy buildings, embodied energy is one of those things that kind of falls by the wayside on this. Part of it is this belief that you see here in the buildings data book that the energy embodied in the building materials is small relative to the energy it takes to operate the building over its lifetime. So we often tend to sort of like say, well, all the energy that I spend on these advanced materials, doesn't even have to be advanced materials, on the materials of my building, on the different technologies, as long as it saves operating energy, I can kind of neglect that because that's the greater good. Well, it's not the greater good. And there was a point when the IPCC finally recognized that, holy cow, we've not been paying attention to embodied energy. And this comes from Working Group 3. This comes out of their latest report, sort of sounding the alarm bell about embodied energy, and sort of something for a little bit tough to go through. The upshot of this graph is they figure by 2050, 30 to 40% of the world's energy consumption will be due to the embodied energy of urbanization, buildings and the infrastructure needed from that, 30%. So this sort of thought that as long as I make my own energy, operating energy for my building, I can make it as big as I want to make it, is sort of missing this whole aspect of it. We have to be as cognizant of those types of consequences as anything else, and sort of like we don't get to sort of like leave out things by justifying them and helping in another range. This is actually something as well that a number of us have been talking about. One of the problems we've had with embodied energy is currently embodied energy is accounted for to industry. So if you look at all the different sectorial accounting for energy, the embodied energy of buildings is counted to industry. And so predictions about embodied energy have sort of followed the fact that industry has remained relatively flat. We know that with developing countries, their industry becomes more efficient, which is, so as people have looked at projections for industry, they've maintained that as relatively flat, not sort of realizing this tie-in that embodied energy is actually there. So as we see rapid urbanization and rapid building, we will see, if it's going to still be under industry, it'll be accounted for there. So many of us feel like these projections really sort of underestimate what the true impact of buildings are going to be. This is my favorite one. This is sort of the whole reason I live, is this aspect. You know, I grew up in a time, did not grow up in a time, but I was educated in architecture at a time when the mantra was integrate everything. That the Centre Pompidou was like the pinnacle of things, that you could see everything. You saw structure, you saw environmental systems, you saw it all out there, was all integrated together. There's no reason for many of these systems to be integrated together. We understand a structural system as being absolutely integral to a building, integral to the form of a building, integral to the actual material artifacts as a building, because that's what it's supporting. There is nothing about an environmental system that has any relationship to those particular artifacts. If we think about the actual sort of energy exchanges that take place, there's really no relationship. And yet we have this desire to sort of like make everything into an architectural material artifact, something that we recognize and something that we see. If we could begin to rethink that environmental systems are not here to serve the building, they're actually here to serve the body, what would they be? How small could they be? How more efficient could they be if they were just doing the precise things that we needed to do? Again, as we've had technological development, this sort of idea of everything sort of combined together into a single system is no longer necessary. We can operate discreetly. That's my heartbreak at LEDs. When I first saw LEDs coming down the pike, you know, more than 20 years ago, I thought this will be our first technology that we can use discreetly and directly, you know. Just those sort of moments in those locations that really deal with vision. This will be easy. It's not going to be like sort of working with environmental systems and heat transfer and fluid mechanics and all the things you have to do for that. It's going to be so easy to work with LEDs, and that's what sort of has me somewhat dismayed to see them simply becoming conventional lighting. But coming back and sort of understanding how we can design these behaviors at the scale at which the behavior occurs and intervene at that scale is where we want to move forward. I think about something like this as a top 10 green building that talks about, in the top 10 green buildings, part of the description for this is how abundantly daylit this building is. All I can think is that poor dog must be dying of heat exhaustion in that location. This is such a belief that we have, that building orientation, that building aperture size is all about how we deal with daylighting. Light is not a building scale behavior, it's a micron scale behavior. You can do everything you want at the micron scale. I have a class, a seminar right now. One of the reasons I couldn't come yesterday is my seminar on light and materials meets from 3:30 to 5:30 on Wednesdays. And you know, the point of this seminar is to work in terms of a complete disconnection between the facade and the light that you deliver, not to connect it to a facade. Show how easy it is to move light, concentrate light, redistribute light over great distances, but it doesn't have to come through the picture plane of glazing. And once you sort of realize that light doesn't have to come from the picture plane of glazing, and that view isn't necessarily related to it, it starts to sort of question the entire idea about that facade. This is one of my favorite LED projects of all time, and while this is not about energy, the thinking here is amazing. Some of you may have seen this incredible Rothko Murals installation at the Fogg Museum at Harvard. Harvard had actually badly managed and stored these Rothko murals. They had become so badly faded, so everything that you see on the right is the current condition of those murals. They spent a great deal of time talking about what they were going to do in terms of this restoration. And they realized that the paint application was such on this that they weren't able to recover any of the original pigment colors. They were going to have to sort of paint on top of them, and they thought that would actually be as destructive to these murals as just to recreate the colors that would destruct as well sort of structural aspects that were critical to these murals. And so what you were seeing there is a digital mapping of light for real on one of the panels of the murals. It happens about an hour every day that they do this to show you how the murals originally looked. Here's Jens Stenger, and he's actually showing you that this is indeed a digital mapping on this. And here we can see part of the program for this. The sort of careful understanding of exactly how every pixel sort of it's not just sort of how everything is sort of mapped onto every pixel, it's understanding how every pixel maps onto the retina so that when you're in that room, there is no way that you imagine that could possibly be a virtual image that you're looking at. It is really not until you block that projection that you realize that that is not paint pigment that you're dealing with, but it's actually sort of reflected light from the LED patterns that are on that. That is obviously a high energy type of thing, but that sort of thought about exactly sort of what it is that's within our view field and ultimately how it maps on our retina. If this is the way that we could think about technology, we have an incredible opportunity to sort of to dramatically change the amount of energy we use, how it gets to the retina, how it deals with the skin. And of course, even things for those of you who are in engineering, and I'm originally a mechanical nuclear engineer, and we used to always joke about how backwards the auto industry was. In architecture, we think the auto industry is amazing. But this is an example of just sort of showing the difference between how we light in a building versus something useful, like a car dashboard, how carefully that has been thought out. The type of analysis or simulation that took place. They used SPIOS. They used SPIOS in order to do micron scale ray tracing in order to know exactly what the backlighting of that dashboard should be, what should be foregrounded within that dashboard, and also sort of understanding those environmental conditions. There's no reason why we aren't doing something like this in buildings. And again, I always say this every time I give one of these, like, there's a lot of lighting on in here. That it's not actually helping you see the screen. There's a lot of lighting going on here that's not performing much of a function. One real quick thing, talking about going discrete, and this is one that I know some of you have seen before because this is near and dear to my heart because it's from my doctorate. When we start thinking about what we can do with different types of technologies, this gets back to the fact of dealing with environmental systems. It's actually not hard to manipulate things like heat transfer coefficients. We look to optimize material properties, a material property of conductivity. Well, I can change conductivity of pretty much any material by sort of understanding and manipulating its context. And it has to do with something we call a characteristic length. And so just real quickly, and I won't talk about this, but characteristic length determines the heat transfer coefficient, the wall function that we have of sort of any kind of convective material is manipulable. I can manipulate it at will. I can manipulate it easily with conventional building materials. You can take a conventional building material and change its heat transfer coefficient, its insulating value, its conducting value by a factor of 10. It's not hard to do. It's not something we do, because it's not part of our standard tools or our standard analysis, but it's really easy to do by simply sort of understanding context that it's in and working in understanding that context. So this is actually a very early series of studies I did of taking a halogen lamp, working with context to create a whole different series of microenvironments within space, within an environment. And so when I look at the types of things that we have available to us in order of conditioning buildings and sort of looking from the air handler, the giant air handler at the left, of which, you know, a typical building will have many of those, to a small heat pipe on the right, what's really hard to get across to many people is that all of these move the same quantity of heat in the same amount of time. I don't mean like relative, I mean absolutely. The heat pipe is moving just as many BTUs per hour as is the large air handler. Only the air handler does so in the most inefficient means known to humankind, and the heat pipe does it incredibly discreetly. The difference is the distance over which they move it. They might move at the same rate, but they're doing it over very different distances. Only the ones on the left can do so for great volumes. The ones on the right are doing so at either a point or across a millimeter. One of the things, and this is the reason why I'll keep harping back to this, because this is what broke my heart when I was doing my doctorate. At the time, the Department of Energy was, this is actually one of their small little sketches. At the time, the Department of Energy was developing micro heat pump wallpaper. They had speculated that micro heat pump wallpaper, about 1 meter by 1 meter poster, was more than enough to heat or cool the average home. They continued to work on it. It was down to 10 centimeters by 10 centimeters, and it was cheap. And within a year, the program was canned. And I had been actually looking forward to it, not to sort of use it in that particular way, but actually to use it to sort of modify heat transfer coefficients. Their response to that was that it wasn't effective, it wasn't that it didn't, you know, that it wasn't cheap and sort of going to be easy to make. It was that the problem with this is that air does not see the wallpaper. You can move, it sort of moves a tremendous amount of heat, but it's only moving that tremendous amount of heat over a millimeter or so. So air doesn't see that wallpaper. And the criteria we're giving is that whatever we were developing here had to match the conditions of a dilution-based HVAC system. And so it's just not going to happen with this. At the same time, I had a visiting scientist position in Korea, and they were trying to do the same thing in Korea at that point, not with microscale, but with mesoscale thermoelectrics. And they also stopped the program there as well when they realized that they couldn't use it to heat or cool a building. I thought, why are you using it in this way? For all the ways I could use something like this, the last way I'd use it is to try to make homogeneous air conditions. You know, the ability to modify heat transfer coefficients would make a stunning difference in the energy use of our buildings. But that belief that what we have and what we know is so omnipresent, so omnipowerful, that we weren't able to do that. So, last few slides, maybe 2 or 3. You know, the funny thing about it is that if we look at all the extant behaviors in a building, all of them are these sort of up and down convective behaviors. These are the ones that are most responsive to sort of small types of perturbations or interruptions. Easy to work on these heat transfer coefficients, easy to take the heat rising or dropping and contain it autonomously, get it out of the building so that you don't mix it into the building. Easy as well to sort of negotiate what's happening around the body. These are the opportunities that we're missing on this. Last slide and a half. This is, if I could sort of one small thing on this, designed for a contingent smartness on a constituent armature. Make as much of the building as dumb as possible, but discreetly look at the technologies that you're working with in order to find those moments, leverage those critical moments where it really does matter to sort of bring the highest level of technology and functionality as possible. The issue is we need to be instrumentalizing the behaviors we want to control. We're not just here to optimize properties, but instrumentalize those behaviors. And this is really my last slide. This is going to take us in a whole other direction. It's one of my favorites. You may not be able to see what's going on here because there's so much light in the room. But when I talk about this sort of idea of things being contingent and constituent, we talk about glazing. The reality is that we might optimize the transparency of glazing. The context of glazing determines whether or not it's transparent. So you see a photo of me, not the woman with the short hair, but I'm reflected off of her coat taking a picture. That same glass that is completely transparent around her, the minute context changes, the veiling changes, suddenly it's a mirror and it's completely opaque. You can see that, right in here. Phenomenon that occurs with pretty much every single thing we have is that behavior is different than properties. That behavior can be contingent upon circumstances. Can we start to sort of leverage, work on, mitigate, operate some of these contexts in order to elicit the behavior even from some of the dumber materials that we work with? Now I'm really done. So thank you all so much, and I'm looking forward to the rest of the day.
Don't go away. Shall we take a few questions? So I want to just echo what Sherry said. Is you're the perfect person to be here with your background in mechanical engineering and architecture, and it was a spectacular talk. So thank you so much for making time to be here today. We have 2 microphones on the floor. Questions? Oh, there must be questions. So not hearing any questions. You're off the hook.
That's usually not a good thing.
Yeah, so come up to the microphone here. Come on, right.
Can you please talk a little more about when you talk about the lighting not through the facade or a pictorial frame by itself, but like from I understand everywhere, or
Yeah, so
about the topic that your class is talking about.
Yeah, so one of the key things in this class is to understand, and it's for architecture students, and very much of this is. Am I supposed to look at this too?
No.
I'm very distracted by things. I'm easily, maybe that's why I want my lighting under complete control. I'm so easily distracted. But the point of this class is actually sort of like to decouple the idea that the things that we make are the progenitors of their own effect, that they cause their own effect. We believe that if we design a facade in a particular way, particularly in terms of a picture plane representation of it, then what it is also what it appears to be, or it's going to construct what it appears to be. And the whole purpose of this class is actually to demonstrate, no, that it might have a small role to play in that, but how something appears to be is driven by a series of these contextual and contingent types of interactions. And so I want to sort of have the students understand that materials are not the cause, but they are instrumental. So the architecture that we make is sort of not its effect. It can, but it can instrumentalize certain behind types of behaviors. And so the end of the class is that they learn how to design for effect and actually sort of come back and understand the material interventions that will enable that type of effect. It's kind of the inverse of how we normally think about architecture. We sort of assume it's going to create its own effect. We spent a great deal of time in the class working with light at the particular scale at which it works with, and sort of also working with materials in it. But it's kind of like a tripartite piece. We deal with designing for perception, understanding the eye, how something arrives at the eye. We designed with the physics of light, and then we designed with materials as the intervention for it. And once you sort of get the idea that it doesn't belong to the major artifacts, but it's actually something minor, not minor, but sort of more discrete, it's surprisingly easy. That may not answer your question, but that's the range in which it goes in. Yes.
So you mentioned 20 years ago you were excited about LEDs. What is the technology that you are most excited about going forward? I know in the next talk we have something, Corning's going to talk about integrating sound with glass. We've got some dynamic facades. What's the next technology innovation?
Well, this is now this is when you're going to be really irritated that you invited me. You know, I taught perhaps in fact I'm sure, the very first class in smart materials at any school of architecture. I started teaching it in '97, and a lot of my background at NASA as well as at DuPont was in material development, so something that I've always felt very strongly about. The interesting thing is I'm moving in the opposite direction. I've become so interested in behaviors and phenomena, how to manipulate those, that even in this class that I teach, which originally began as a class in smart light, is now one in which for everything that they make, they have to be able to create the same effect through multiple means, including the dumbest possible combination of materials. So I would say that while deep in my heart, I still know that we can revolutionize a major part of building industry, as well as how we actually sort of like feel in a building by discreetly working with LEDs. I have not lost my faith in their potential. I'm also spend more time now thinking about the physical phenomena themselves than I do as much about sort of the tech. I want the technologies to be instrumental. So I'm more excited about the phenomena, then I want to find the technologies that will instrumentalize that phenomena. Okay.
So thank you again for being here and having a terrific talk to get us started today. I'll just say at the end of the day, there's a keynote speaker at 4:45 who will complement your talk. We'll have a presentation by a program manager from ARPA-E. This is the Advanced Research Project Agency of the Department of Energy. We'll give an insight into how ARPA-E is encouraging the development of new technologies relating to buildings and energy, and specifically this program manager is interested in technologies at the point of use for the occupant. So that talk promises to be very interesting to complete our day. So now we're about to begin our parallel sessions. So we'll have 3 tracks. We have the design track, the energy track, and the futures track. As noted in your program, the design track will start in this room at 9:45, and then subsequently, beginning in the second session, the design track will be in the Pompey room, which is up the hall. The energy track is in the Camillus room, which is out of this room. Make a left and then a right. And then the futures track is in the Skaneateles room, which is out of this room. Make a left and a left. So Skaneateles room, Camillus room, Pompey room, and you're in the Lafayette room. So with that, let's all break and go to our respective rooms. Come back here for lunch at 12:30, and there'll be presentations by students who won in the poster competition last night at lunchtime. See you back here at lunch.